What's up guys, welcome back to my channel. Today we are solving paper 4 math, which is a mechanics paper. We are solving a 2019 paper which is totally random, October 2019, paper 4-1. If you want me to solve any particular paper, you can just comment down below. So guys, without further ado, let's begin. A crane is lifted A crane is lifting a load of 1250 kg vertically at a constant speed of this. Given the power of the crane is a constant 20 kilowatt, find the value of V. Alright, so let's see. We have this load L, which is being lifted up vertically with a constant speed of V meter per second, and the weight is 12,500 Newton. So since the velocity is constant, there would be an equal force being applied by the crane, which is 12,500 Newton. So we know that F by the crane is 12,500 Newton, and the power of the crane is constant. We just have to find the value of this velocity. So we have this formula: power equals energy upon time, which is, let's take work done, and work done is basically force into distance upon time, which is force into velocity. So we have uh, power equals force into velocity. This is the main formula. You don't actually need to show the derivation part, this is just for your understanding. So we have 20,000 watt equals 12,500 multiplied by V, and V is gonna be, so I'm just using my calculator. V is going to be 1.6 meter per second. So this is the first question's answer. Now moving on to the second question. The total mass of a cyclist on a bicycle is this. So we have this. Cyclist ascends a straight hill of length 0.7 meters. So straight hill of length is inclined at 1.5 degree to the horizontal. So we have this hill, which is 0.7 kilometer, which is 700 meters. So we have this as 700 meters in length, and it's inclined at 1.5 degree to the horizontal. Her speed at the bottom of the hill is 10 meter per second. So when the cyclist is here, the speed is 10 meter per second, and at the top of it, it's 5 meter per second. So when the cyclist is here, velocity is 5 meter per second. There's a resistance to motion, and the work done against the resistance that the cyclist ascends the hill is this. So work done against friction is simply 2000 joules. Cyclist exerts a constant force of magnitude F Newton. So F Newton is going to be in the upwards direction. So we just have to find this F. So I think, guys, there are two ways to solve this. One is using the force method, and the other is using energy. But I guess in this case, the energy method would be a bit simple, because we already have this work done against friction, which is 2000 joules. So all we have to do is just form an equation and conserve energy. So let's say, as the cyclist ascends, as it goes to the top, the GP is increasing. Means yeah, so GP is increasing, and work done against friction. Actually, if you see, as the cyclist goes on top of the hill, the distance keeps increasing from the starting point. So that's why even the work done uh, due to friction keeps increasing from the bottom to the top, and exactly on the top, the work done against friction in total is 2000 joules. So even work done against friction is increasing as you go on top of the hill. But if you see, the velocity is decreasing, correct? It goes from 10 meter per second to 5 meter per second. So kinetic energy is decreasing. So we just have to equate the magnitudes of these. So what's increasing, the magnitude of what's increasing should be equal to the magnitude of what's decreasing. So uh, we'll use mgh for gp, where h is vertical height. So for we can just use 700 sine 55. So h is equal to 700 sine, sorry, 1.5. Trigonometry. All right, so we just have to find this h, and work done against friction is 2000, and kinetic energy is half into m into v square minus u square, which is basically delta ke, actually the change in kinetic energy, which is half m. Now since you're only concerned with the magnitude, we'll have to take the velocity with the bigger value first. So 10 square minus 5 square. So it all comes down to this final equation, which is m into g into h plus 2000. uh, oh guys, I actually forgot to include this, because the constant force of magnitude f newton in the direction of the motion. So even f newton, if you see, the distance is increasing. The formula for work done by this force f is equal to f into d, where d is the length, which is 700 meters. So even this is increasing, so we'll include this on the left hand side. So this plus uh, f into 700, which is, this is equal to half into 75 into 10 square minus 5 square. Alright guys, I hope you understand this, because this is just gpe plus uh, work done against friction plus uh, the work done by force F. So if you calculate, yeah, so you get F has 18.5. So we actually get F as negative 18.5. So let's see what mistake we have made. It's evident that we have made a mistake in this part. F should actually have been here, but let's see why. So well, I think that the silly mistake that I made is that Actually, if you see this constant force of magnitude F Newton is actually the force exerted by the cyclist, which will actually reduce in magnitude because the cyclist will the work done by the cyclist will actually keep decreasing. You know, uh, if he keeps losing the energy that he applied on the cycle as he goes to the top, the magnitude will actually decrease. So that's why we got F as negative 18.5, which is wrong. uh, F into 700, this term should be over here, so it should actually be plus 700 F. I hope you guys understand, because if you see the energy spent by the cyclist or the work done by the cyclist keeps decreasing. He has only applied a constant force of magnitude F throughout the journey. So let's move on to the next question. A block of mass 3 kg is at rest on on a rough plane inclined at 60 degrees to the horizontal. So again we have a plane 60 degree to the horizontal. Okay, a rough plane. A force of magnitude 15 Newton acting. Wait, hold on. So first we have this mass 3 kg. So weight is 30 Newton. 30 newtons. A force of magnitude 15 Newton acting up the line of greatest slope of the plane is just sufficient to prevent the block from sliding. So 15 Newton is acting up the line. So up the slope we have 15 Newton. Okay, it says that it's just sufficient to prevent the block from sliding down the plane. So if the block is about to slide down, frictional force which opposes this downward motion will act upwards. So actually this is the 15 Newton force. We'll resolve this weight component first. So down the slope we get uh, 30 sine 60, and as I said, the friction will oppose the downward motion. So you have frictional force. So Ff is just frictional force. So it just prevents the block from sliding. So forces are actually balanced. So 30 sine 60 is equal to Ff plus 15 Newton. Now we'll have to use uh, the other weight component, which is the cos component. So this way would be 30 cos 60. We'll have to find this because uh, ff that we get, which is 30 sine 60 minus 15, is actually equal to mu naught Fn, because ff friction force is actually mu naught Fn, and Fn actually acts this way. So if you see when the vertical forces are balanced, so Fn is equal to 30 cos 60. So we have 30 sine 60 minus 15 is equal to mu naught into 30 cos 60. This frictional force is actually this. So if you solve for mu, you will get, let's see, we'll get 0.732. So this is actually a simple question. The force of magnitude 15 Newton is now replaced by a force of magnitude x Newton acting up the line of greater slope. So we have the same slope, but the 15 Newton force is replaced by force of magnitude x Newton. So this is the block. This is uh, The weight was 30 Newton, correct? Yeah, 30 Newton. So this component would be 30 sine 60, and there's this force x over here. Find the greatest value of x for which the block does not move. So for x to have the greatest value, like see, there are two possible cases. One where the block moves downward, and one where the block moves upward. So for the block moving downward, the case would be like this. We have x, we have friction, and we have the weight component. If you see, we'll actually have this x plus frictional force is equal to the weight component, which is 30 sine 60. But since you want the greatest value, if you see the block moving upwards, x still acts in the same direction upwards and the weight component is downwards. If let's say the block is moving upwards, now initially we just considered it moving downwards. Let's consider it's moving upwards. The frictional force will now be downwards because it will oppose the upwards motion, and since frictional force is now downwards, the final force equation that we get is going to be x equals ff plus 30 sine 60. Now guys, why don't you decide and tell me mathematically which equation will give you a greater value for x? Of course it's the second one, so we'll use this. So x is equal to, if the frictional force is uh, frictional force is going to be mu naught Fn, which is 0.732 into 30 cos 60. I hope you guys know that how, because we have this cos component, we have the frictional force here, so we have the normal force over here, so frictional force equals mu naught Fn, which is the normal force, correct? So this is mu, this is normal, plus 30 sine 60. If you solve this, we'll get x is equal to 37 Newton. Moving on, two blocks and we have masses 4 kg and 5 kg respectively are joined by a light and extensible string. I just don't know what's up with this paper. I mean, there are very many slope questions. The block rests on a smooth plane at an angle alpha to the horizontal, where tan alpha is 7 upon 24. So we have alpha is tan inverse of 7 upon 24. The string is parallel to a line of greater slope on the plane with of the plane with B above A. A force of magnitude 36 Newton acts on B, parallel to the line of greatest slope. Alright. Find the acceleration of the blocks and the tension in the string. So first things first, there's a simple way to just find the acceleration. We can consider the whole system. So if you look with respect to the whole system, there's tension force in this rope, T and T, which effectively get cancelled because we are considering the whole system here just to find the acceleration. So both of these t are in the opposite direction, so they get cancelled. We have one force due to 4 kg downwards, the weight component of 4 kg, and we have the weight component of 5 kg, and that is the only downward force. These are the only downward forces, and the upward force is 36 Newton. So if we consider the whole system, and if we have to apply the formula F equals to ma on the whole system, we'll need the resultant force on the whole system, which is going to be 36 minus the total of the weight components of both of them. So it's going to be 40 sine alpha plus 50 sine alpha. I hope you guys get it how, because we have this block right here, uh, this block A, 40 Newton force exactly downwards, so this component is going to be 40 sine alpha. Alright, similarly we do this with block B, and this is 50 Newton, this is going to be 50 sine alpha. Both of these are acting downwards, and we'll have to balance it with we have to find the acceleration, so we'll find the resultant force by subtracting 36 Newton minus this. So you get 36 minus (25.2), which is 10.8 Newton. Now coming back to the fact that I have taken the whole system. Since you have taken the whole system, we'll have to again um, find the total mass of the system, because if we use this formula, so the total mass is going to be just 4 plus 5 kg, the two blocks, which is 9 kilograms. So we can just use this formula to find acceleration. 10.8 equals 9a. I hope you guys know that the F in this is actually F resultant equals ma. So A is 1.2 meter per second, and yes, A is going to be the same for both, because both of them are being carried by the same strings. So B moves just as much as A does, so their velocities, their acceleration, and the displacement all are going to be the same. Now coming back to the tension in the string part, so we just have to find this value of T. So we can just take any of the one block. Let's say I'm taking the 4 kg one. So remember from the diagram that I just drew, we have this the 4 kg block, we have 40 sine alpha, the downward component, and then we have the tension force pulling upward. I hope you all guys can understand. We have this tension force pulling upwards on A. So I guess these are pretty much the only forces, because we don't have to consider friction over here. And we have the acceleration of both the blocks. So even for the 4 kg block, acceleration is going to be 1.2 meter per second square. So we can just use F equals ma again. So T minus 40 sine tan inverse of 7 upon 24. This is basically alpha is equal to m into a. Now we are only taking the 4 kilogram block into consideration. So this is going to be 4 into 1.2. m into a. So if you solve this, you get tension as 16 Newton force. So we have the acceleration and we have the tension. Let's move on to the next question. Okay. At a particular instant, the speed of the blocks is 1 meter per second. Yes. Find the time after this instant that it takes for the blocks to travel 0.65 meters. So it's actually kind of simple because we have the acceleration from the previous question, from the previous slide, which is 1.2 meter per second square. We know the distance it has to travel is 0.65 meters, and at a particular instant, the speed of the block is this after this instant. So initial velocity is 1 meter per second. We just have to find the time it takes to cover this distance. So we can just use s equals ud plus half at square. So 0.65 is equal to 1 into t plus half a into t square. We'll get a quadratic, so 0.65 equals 1 plus 0.6, sorry, t plus 0.6 t square. So 0.6 t square plus t minus 0.65 equal to 0. So we'll get t as 0.5 seconds or negative 1.3 seconds. But guys, I mean, can time ever be negative? No, right? So we'll not take this. Our only answer is t is 0.5 seconds. So now comes an equilibrium question. A small ring P is threaded on a fixed smooth horizontal rod AB. Okay, the three horizontal forces of magnitude this act on P. Given that these three forces are in equilibrium, find the value of F and theta. Okay, so these three horizontal forces act on P such that they are in equilibrium. So sum of horizontal forces is equal to 0 and sum of vertical forces is also equal to 0. So we can form two equations to find f and theta. Like just to find two variables we need two equations. So first let's take the horizontal components. So I hope you all know that, let's say if you have this f and this is theta, so if you resolve this you'll get uh, f sine theta, and this is going to be f cos theta. Similarly, we have over here the vertical component is going to be f sine theta, and the horizontal component is going to be f cos theta. So, well, now we just have to solve. So we'll do that for all the other forces. So let's take the horizontal ones first. So f cos theta, forces in one direction are equal to the other direction. So f cos theta is this way, and the other two forces horizontal direction are in the other way. So f cos theta is equal to 4.5 cos 20 plus 7.5 cos 60. I hope you guys understood how, because if you resolve both of these forces, you'll get 4.5 cos 20 And if you resolve 7.5 Newton, you will get 7.5 cos 60 in the horizontal directions. So you get this one equation, and the other is f sine theta plus 4.5 sine 20 is equal to 7.5 sine 60, the vertical one. So this is vertical, this is horizontal. So all you have to do now is just solve, because you have two equations and you can just solve them simultaneously. So I think one thing you can do is you do f sine theta upon f cos theta, which is equal to tan theta, which is equal to, okay, if we solve this we get f sine theta is equal to 7.5 sine 60 minus 4.5 sine 20. So 7.5 sine 60 minus 4.5 sine 20 divided by the horizontal, which is 4.5 cos 20 plus 7.5 cos 60. So if you solve this for tan theta, you will get, tan theta is equal to 0.621. And if you further solve to find theta, so theta is just going to be tan inverse of 0.621, which is equal to 31.8 degrees. And then to find the value of f, we can just use one of the equations. So we have f cos theta is equal to 4.5 cos 20 plus 7.5 cos 60. We already found the value of theta. We can just uh, substitute this value for theta over here, and we can find f. So turns out that the f value is actually, I'm just calculating, 9.39. I hope you understood this. Now it is given instead that the values of f are this and this, reflected in the acceleration of the ring is this. Okay, find the mass of the ring. So we can use this formula because acceleration, mass and forces come into the picture in this formula. So find the mass of the string. Okay, so we just have to use Fm equals F resultant upon acceleration, and we'll only have to use the forces in the horizontal direction. I'll tell you why. If you see, the ring cannot actually accelerate vertically, can it? The ring cannot move vertically. It can only move sideways because it's on this rod AB. So this acceleration, no doubt, is only given for the horizontal direction. So in the horizontal direction, we'll simply find the resultant force, which is F cos 60 minus 4.5 cos 20 plus 7.5 cos 60, because both of these forces are in the same direction, which is towards the left, but this force is towards the right, so we just have to subtract. And don't worry if you get the value as negative, we'll just consider the magnitudes. So Yeah, f cos 60, which is the values of f and theta are given here. So 9.5 cos 30. Okay, my bad. This is actually theta, f cos theta. 4.5 cos 20 and 7.5 cos 60. Divided by the acceleration, which is 1.5. Again, we are just concerned with the magnitude. So we'll just use the magnitude, not the direction. This is going to be cos actually, because we are considering the vertical. So m comes out to be 0.166 kilogram. So I hope you guys understood this. Let's move on to the next question. Yeah. A particle of mass 0.4 kilogram is released from rest at a height of 1.8 meter above the surface of water. Okay, so there's no instantaneous change of speed when the particle enters the water. Water exerts an upward force of 0.56 Newton, 5.6 Newton on the particle when it when it's in the water. Find the velocity of the particle at the instant when it reaches the surface of the water. So it's not in the water right now. So let's say we have this cliff and we drop a particle from here, and the height is 1.8 meters. That is water over here. And mass is 0.4 kilogram. Height is 1.8 meters. So let's see, we have the height. We have height is 1.8. We know 1.8 meters. We know right now it's only under the influence of gravity. So A, and this height is actually equal to the displacement. So A is G, which is 10 meter per second square, and we just have to find the final velocity when it completely covers this distance, when it completely covers this height of 1.8 meter, as soon as it touches this water surface. So we just have to find V. Let's see which formula. We can use V square equals U square plus 2AS. Alright, so V square equals U square is actually going to be 0, because initially it was just released from rest. So initial velocity is 0 plus 2 into A into S. So V is equal to 6 meter per second. Alright guys, so this was just a 2 marks question. Find the time that it takes for the instant when the particle enters the water until it comes to rest, instantaneous rest in the water. You may assume that the tank is deep enough so that the particle does not reach the bottom of the tank. So we have to find the point in time when the velocity is 0. We know that when the particle is inside water, it just enters water with speed of 6 meter per second from the previous question, and water keeps exerting a force upward of F, which is 5.6 if I'm not wrong. Yep, 5.6 upward force. So we clearly know that since the particle is actually having a downward motion and force is acting upward, so acceleration is going to be negative, which is deceleration, which is eventually going to stop the object. So at a point in time inside water, the velocity will become zero, which is instantaneous s. We have to find the time when that happens. So we know v is equal to zero. Initial velocity when it just enters water is 6 meter per second. Now I think we'll have to find acceleration. So first we can find acceleration using F equals ma. So F is just 5.6, the only force acting. And yeah, there is even force due to gravity, the resultant force. So 5.6 minus the force due to gravity, which is mg, which is 4 Newton. Using this, is equal to 0.4 a. So a is equal to 4 meter per second square in the upward direction. Now even if you see this upthrust, which is 5.6 Newton, is actually greater than 4 meter, which is actually greater than the weight. So anyways, we know that this is going to be deceleration, which will stop the object down. So we got a as we got a as 4. We'll actually use a is negative 4 meter per second square because the object is decelerating. So yeah, we can just use uh, v equals u plus at. So t equals v minus u upon a, which is 0 minus 6 divided by minus 4, which is 1.5. Yeah, 1.5. Sketch velocity time graph for the motion of the particle at the instant which it is released. So see, when it we just have to sketch a velocity time graph. So one thing we have to keep in mind is is that the gradient will actually give you acceleration. So yeah, we know that it reaches water with a velocity of 6 meter per second. So let's say this is that velocity, 6 meter per second. So yeah, this is, by the way, velocity in meter per second, and this is time in second. So this is the 6 meter per second mark, and the gradient is acceleration. Initially, till it reaches the water surface, acceleration, which is gradient, is just the value of g, which is 10 meter per second, which is constant. Means the gradient is also constant, and in this case the object is being accelerated, so the gradient is going to be positive. There is positive acceleration. So it starts from rest, which means it starts from 0 and it goes up till this point. This is a straight line where the gradient is g, which is 10. It comes up to this point, which is 6 meter per second, but we'll also have to find the time t. So this is basically the time when it actually touches the water surface. We can just find t using this b minus u upon a, which is 0 minus 6 minus 0 divided by 10, which is 0.6 seconds. So the time it takes for the particle to reach the water surface is 0.6 seconds, which is this. Now the particle starts decelerating until it comes to rest. So we know one thing for sure, that there's deceleration, and deceleration means A is negative, which means gradient is negative. So there's a downward curve, downward line until velocity is equal to 0. So let's say it starts from it will continue from 6 and will reach 0. This one we just have to find the time t. We know that uh, it's taking 1.5 seconds from the moment it touches the water surface. So this this time t2 is actually going to be 1.5 plus 0.6, because it's actually after the 0.6 seconds have elapsed. So this is going to be 2.1. So I hope you guys got this, because this is actually an interesting question. If you have any doubts, you can just comment down below. Finally, we come to some calculus. Particle moves in a straight line starting from rest. Point O comes to instantaneous rest at point P. The velocity of particle at time t seconds after leaving O is v, where v is this. Show that the distance OP is this. So we can use this equation to find the distance using integration, because area under graph of velocity versus time actually gives distance. So we just have to use this, but first we'll have to determine this limits, these limits. So we know it starts from rest, so it starts from time t equals 0, but and it comes to instantaneous rest at point P. So point P, which is our final destination, is again where velocity is equal to 0. So 0 is equal to 0.6 t square minus 0.1 t cube. We can just find the time at which velocity is 0, and if we solve this, we'll get t is equal to 0 and t is equal to 5 seconds. We have already actually taken this, because initially when it was at rest, velocity was 0, but even when t is equal to 5 seconds, velocity is 0. So this limit is going to be 5. So we just have our integral ready. So s is equal to 0 to 5, 0.6 t square minus 0.12 t cube dt. We'll just integrate. We have 0.6 t cube upon 3 minus 0.12 t4 divided by 4 from 5 to 0, which is 0.6 5 cube upon 3 minus 0.12 upon 4 into 5 raised to 4 minus the one with the lower limit, so 0.6 upon 3 into 0 cube minus 0.12 upon 4 into 0 raised to 4. This term is basically 0. So for this term we'll just use a calculator. So we get 6.25 meters, which is what we had to prove. Yep, this is what we have to prove, 6.25 meters. So on another occasion, the particle also moves in the same straight line. On this occasion, the displacement of the particle at time t seconds after leaving O is s meters. So at time t, displacement is s meters, where s is this. It is given that a particle passes point P with velocity 1.25 meter per second at time t equals 5. So mm, we know that velocity is the derivative with respect to time of displacement, which is equal to 3kt square plus 5 ct raised to 4. This is basically v of t, which is velocity. And when time equals 5, the velocity is 1.25 meter per second. So v of phi is equal to 1.25 is equal to 3kt. 3k into t is 5. 5 square plus 5c into 5 raised to 4, which is 1.25 equal to k plus 3125c. This is the first equation, and we'll have to somehow find another equation. Okay, I got one. So particle moves from O to P, and we know that O to P distance is 6.25 meter from the last part. So s of 5 means the displacement at 5 seconds, which is basically at P starting from O, is equal to 6.25 is equal to k into 5 cube plus c into 5 raised to 5. So 6.25 is equal to 125k plus 3125c. So I guess if you just simultaneously solve this, these two equations, these this is the first equation and this is the second equation. If you simultaneously solve these, you'll get k is equal to k is equal to 0.1. Sorry, I'll just write with blue. K is equal to 0.1 and c is equal to minus 0.002. So done with this. Find the acceleration of the particle at time t equals 5. So we know that uh, the gradient of velocity versus time gives you acceleration. V of t from the previous part was 3kt square plus 5ct raised to 4, which is 3 into 0.1 t square plus 5 into minus 0.002 t raised to 4. So a of t is equal to the derivative of this equation, which is 2 into 3.1 t minus 4 into 5 into 0.002 t cube. So, and we just have to find the acceleration at time t equals 5. So a of 5 is the derivative of velocity at time t equals 5, which is 0.6 into 5 minus 0.0 sorry 0.045 cube, which is -2. I hope you guys understand why we cannot use the Stewart equations that we have. For example, s equals ut plus half at square, or v square equals u square plus 2as. We cannot use these equations over here because acceleration is not actually constant. Acceleration keeps changing with time. In these equations, um, in these Stewart equations, we actually consider acceleration to be constant. But over here, in these kind of questions, you actually have an equation for acceleration. Let's say you have 5t, means as the value of t changes, even the value of acceleration changes. So acceleration is not constant. You cannot use this over here. So guys, we are done with the paper. So here I end my video, and thanks for watching. Please consider liking and subscribing, and wait for another video on my channel, GCSE Paradox. Signing out.